going to look at what it means to be an eigenvector or an eigenvalue of a square matrix A. So the first thing that I want to bring up is the fact that you can only have eigenvectors and eigenvalues of square matrices. So A must be an n by n matrix. Okay. To look at what an eigenvector and an eigenvalue of a matrix is, you always have to remember the same equation. And that is A times X is equal to lambda X. So for the n by n matrix A, such that we can find an X and a lambda for which this is true, then X is an eigenvector. So that would be a column vector with n entries in it. So it's an n by 1 vector. So it has n entries in one column. And lambda is the eigenvalue. And all that is a real value. So it's just in R. Okay, so it's not a vector, it's not a matrix, it's just a real value. So if we can find a vector and a scalar for which this is true, then X would be the eigenvector and lambda would be the eigenvalue. What we're going to look at in this chapter is how we can check whether a particular vector is an eigenvector of A and whether lambda is a particular eigenvalue. So we're only going to be checking for values and vectors to see if these are eigenvectors and eigenvalues of the matrix. But in the following chapters, what we're going to look at is how we can actually find the eigenvectors and eigenvalues of a matrix. But we're just checking to see if they are at this point. So if we want to see if X is an eigenvector of A, so if they give you if you're given a vector X that's in Rn, to check that it is an eigenvector of A, all you have to do is do A times X. And if you get back some multiple of that vector X, then you know that it is an eigenvector of X. So if you do A times X, if this is a multiple of X, then you know it's an eigenvector. Okay, so all you have to do is A times X and just check that you get back a scalar multiple of the vector that you started with. So let's say you had a matrix and you wanted to check if 1, 1 was an eigenvector for it. If you got a vector back that was, let's say, 3, 3, well, 3, 3 is just 3 times 1, 1. So it is a scalar multiple of the vector that you started with, so you know that it must be an eigenvector. If you want to check if lambda is an eigenvalue of A, this is slightly more complicated. You start out with, you know that this must be the formula that it satisfies, okay? I'm going to rearrange this slightly, and I'm going to bring everything onto the left-hand side. So my right-hand side now is just equal to 0. Now what I'm going to do is pull out a common factor of that vector X. The problem is, if I did that, I'll put this as a side note over here. If I had A minus lambda times X is equal to 0, the problem that you have is this part here, because you've got a matrix minus a scalar. So therefore the dimensions don't match. So I can't do one minus the other. But what I can do is I can say, okay, I'm going to do A minus lambda times the n by n identity matrix. So what that does is it's going to scale that identity matrix by that factor of lambda. So all it's going to do is basically make sure that the dimensions match. So Then you have an n by n matrix minus an n by n matrix, and then you can multiply that by the n by 1 vector. But just to make sure that you have the dimensions correct so that you can do one minus the other, you have to make sure that you multiply it by the identity matrix. So when we factor it out, we're going to get a minus lambda I times x is equal to 0. So if you want to check if lambda is an eigenvalue, all I want you to do is to calculate a minus lambda I. So you get your matrix A that you start with that they give you in the problem, and you're going to subtract lambda I from it. So if they say, here is a matrix A, check whether, let's say, lambda is equal to 3 is an eigenvalue. All you're going to do is do the matrix A minus lambda times I, or 3 times I in that case, and you will get a matrix back. What it will effectively do is subtract that eigenvalue off of each element in the diagonal of A, as you'll see that in an example in a second. So we're going to call that matrix B. Then what I want you to do is you're going to take that matrix that you get, that resulting matrix, and you need to solve this system. So you're going to have a matrix that you'll get with A minus lambda I. You'll call that matrix B. And what you want to see is if this thing has a non-zero x value. We do not count the 0 vector as an eigenvector. So that is a good point to make. Do not count 0 as an eigenvector. Okay? We want it to be a non-zero vector. So what you need to look at is not just whether you can find a vector, because this is a homogeneous system here, okay? It's always going to have 0 as a value, well, as a vector that would give you a solution to this thing, okay? 0 vector is always going to be a solution. What you really want to find is whether there is a non-zero vector for which this holds. So you want to see if there is a non-zero vector for which this is true. If you can find a non-zero vector for which this is true, that vector would be an eigenvector of the matrix A, okay, because it's going to satisfy that AX is equal to lambda x. So if you can find a non-zero vector for which that is true, that means that it is an eigenvector. That means that lambda is an eigenvalue. So what I want you to do, if you have a non-zero vector for which that is true, that must mean that that system has free variables in it. If there is a non-zero vector for which this is true, that means there are free variables in the system. Okay. Just as a side note, any vector x that you can find that satisfies this equation such that that vector is non-zero. So any vector that you can find that is non-zero, that satisfies this particular formula, is said to be in the null space of this matrix. Okay, so if you can find an x that lands in there, then it would be in the null space of B, or in the null space of A minus lambda I. So any x that satisfies this, not only is it an eigenvector, but it is also in the null space of A minus lambda I. okay, because I can take a minus lambda I, multiply it by that vector, and end up back at 0. So that vector will be mapped to 0 by a minus lambda I. There's another name that we have for this. The null space of a minus lambda I is actually the eigenspace of A. Okay, if we actually go back here, because there are free variables in this system, that must mean that there will be infinitely many solutions to this. So if you can find a free variable and hence there will be a non-zero vector x that satisfies that, there will be infinitely many x's that satisfies that. Okay, so you either have just the 0 vector satisfies that, which isn't an eigenvector, we don't count the 0 vector. But if you can find something that is non-zero that satisfies this, that must mean that there are infinitely many vectors that satisfy that. So because there are infinitely many of them, we take that whole space of them, so all of the vectors that satisfy that, and we put them as an eigenspace of A. Okay. We're going to do a quick example. So the question is lambda equal to 3 an eigenvalue of this matrix? Okay. And if that is the case, we're going to find the corresponding eigenvectors. Okay, what you should find, for each eigenvalue that you have, there will be eigenvectors. So there will be eigenvectors associated with the eigenvalue. And for each eigenvalue that you have, because there is normally more than one eigenvalue for any matrix, you can have repeated eigenvalues that we'll look at later. But you normally have more than one eigenvalue for a matrix. So for each eigenvalue that you have, there will be an associated eigenspace of A. There will be associated eigenvectors. Okay, so let's check whether lambda is equal to 3 is in fact an eigenvalue. So we know that we have to plug it into here and see if there is a non-zero vector x such that that is true. So we need to find a non-zero vector x such that when I multiply that vector or those vectors by a minus 3i, I'm going to get the 0 vector. Let's first figure out what a minus 3 times the identity is. So that will be 1, negative 1, 1, negative 1, 1, negative 1. And then minus 3 times the 3 by 3 identity would be that, which should give me negative 2, negative 1, 1. And 1, negative 1, negative 2. Okay. So what I am then trying to solve is this system. So if I'm trying to solve that system, I'm going to create an augmented matrix and reduce it down to try and solve for x. And if you do that, again, you can type this into a calculator to find the reduced row echelon form. What you end up with is this matrix. Okay. Now we already know that we have a free variable here, okay? There is no pivot in my third column. So I know that x3 is a free variable. So I already know that there are going to be non-zero vectors that satisfy the original formula that I had here. Okay, because I've got free variables, there is a non-zero x for which this is true. So I know that I'm going to get an associated eigenspace for A. I'm going to get associated eigenvectors. So therefore, we already know that lambda equals 3 is going to be an eigenvalue of A. So we already know that there is a free variable. x3. Hence, there is a non-zero vector x for which a minus 3i times x is equal to 0, which means lambda is equal to 3 must be an eigenvalue of A. Okay, now the question is, what are the eigenvalues, the eigenvectors that are associated with the eigenvalue lambda is equal to 3? Well, what we're going to do is we're going to find out from this matrix here, as we normally do when we solve a system. So we should find that x1 minus x3 is equal to 0. Let's come back here. And from the second line of that matrix, we get x2 plus x3 is 0. And then there are no pivots in the third column, so we know that x3 is free. So I'm going to rearrange these to be in terms of my free variable. So I get x1 is equal to x3, x2 is negative x3, and x3 is free. So my solution x in terms of x3 is going to be 1, negative 1, 1. So my eigenspace is all scalar multiples of this vector. Okay, x3 can equal anything. So my eigenspace of A in association with lambda is equal to 3 is going to be all scalar multiples of this vector. Therefore, one particular eigenvector, so a particular eigenvector of A associated with lambda is equal to 3 is the simplest possible scalar multiple of that vector, which is itself. But another eigenvector of A associated with lambda is equal to 3 could be 2, negative 2, 2. Okay, I can take any scalar multiple of that vector. I can let x3 equal to anything, and it will still be an eigenvector associated with lambda is equal to 3. So I know that that vector, go back, that vector will satisfy that equation. Okay, so what that tells me is that multiplying any of those vectors, any scalar multiple of this vector, multiplying that by A is the same thing as multiplying that vector by 3. So I can either multiply it by A or multiply it by 3 and I will get the same answer. Okay, but I can take any scalar multiple of that vector and that would be true. So keep that in mind when you do these. I will actually write the eigenspace out just so you can see how it is written. So this would be a particular eigenvector. We'll call it V, you could call it X if you liked. That would be a particular eigenvector. The eigenspace has a basis So all you would do, okay, sometimes you have more than one free variable. So you would have more than one vector within your basis of the eigenspace. So whichever vectors that you get, so you could have, if you have more variables here, you could have x3 times a vector. Let's say x4 was also another free variable. You could have plus x4 times a vector. I could take any scalar multiples of those vectors, any linear combination of those vectors, in fact, and it would be an eigenvector associated with that eigenvalue. So my eigenspace has a basis of those vectors that I get. Okay, I know that those vectors will be linearly independent from one another. Okay, we looked at that previously when we looked at the vectors in the null space of a matrix. So as these are in the null space of A minus lambda I, we already know that they're linearly independent because they're in a null space. So whichever vectors that you get here, you could have, like, let's say plus something else times a vector plus however many free variables with a vector that you have. Each one of these vectors will be linearly independent from one another, and they span that null space of A minus lambda I. So they span my eigenspace of A. So when you write the eigenspace, you will always say that the eigenspace has a basis of those vectors. So if you have more vectors over here, they would also be included in your basis of the eigenspace of A. So as I said, what we have done here is we have looked at how we can find whether lambda is an eigenvalue of A and whether x is an eigenvector of A. What we will actually look at next time is how we can actually find lambda and x. So all we have done in this chapter is to check whether they are eigenvectors or eigenvalues, but next time what we're going to do is actually to find them ourselves. Just as a quick side note, there are some simple matrices where it's really easy to pick off what the eigenvectors and eigenvalues are. So one of those is for a triangular matrix, whether that is upper or lower triangular. The eigenvalues of a triangular matrix, so this is off of the main diagonal. Okay, so if you have a matrix where that is your diagonal, okay, so that is your diagonal. So a triangular matrix either has elements on the diagonal and then up here, or it has elements on the diagonal and down here. Okay, but it's always off of that main diagonal. Don't take the diagonal this way. Okay, it's always the diagonal this way. So the eigenvalues of some triangular matrix, we'll take it as upper triangular for now, just so we can see what we're looking at. The eigenvalues are just the entries that are on that main diagonal. So the eigenvalues are just the entries of the matrix along that main diagonal. If an entry occurs more than once, that just means that it is a repeated eigenvalue, which we'll look at more as we go through this chapter in chapter 5. But it is possible to have a repeated eigenvalue. There's just more to do with their eigenvectors that we will have to look at, but you do still count them almost like more than once in a way. Okay, so it doesn't matter if some of these entries are repeated, they are still eigenvalues. Now, this is a theorem that I want to go through with a quick proof. For this one, there is a proof in the textbook, but it's actually really easy to see. Once we start calculating eigenvectors and eigenvalues, it's actually really easy to see that this is the case when we actually calculate some of this stuff. But if you would like to look through that proof, it is in the textbook in 5.1. So the last theorem that I want to go through for 5.1 is looking at when you would have an eigenvalue of 0. So we know that we never use an eigenvector of 0. Okay, we don't count 0 as an eigenvector. But what we do look at is an eigenvalue of 0. You can have an eigenvalue of 0, but it only occurs in certain cases. And that's what I want to look at for this last theorem. So the matrix A has an eigenvalue of lambda is equal to 0 if and only if A is not invertible. So the only time that you should find a 0 eigenvalue for a matrix is if that matrix is not invertible. On the other hand, if A is invertible, we already know that 0 will not be an eigenvalue. Okay, so it works both ways. So let's look at a proof for this. It's a pretty short proof. 0 would be an eigenvalue of A. Okay, looking at our definition, 0 is an eigenvalue. I'll call it an E value just to shorthand it. 0 is an eigenvalue of A if and only if that equation is true. Okay, that's the definition of an eigenvector and an eigenvalue. Well, if I take 0 times a vector here, that's just a 0 vector. So that means that A times X is equal to 0. So I know that 0 is an eigenvalue of A if and only if that is true, and if and only if this has a non-trivial solution. So 0 would be an eigenvalue of A if and only if has a non-zero or a non-trivial solution. So if I can find a non-trivial solution X such that A times X is equal to 0, well, that must mean that it has a free variable. Okay, if it's got a non-zero solution, then A times X is equal to 0 has a free variable. So there's going to be a free variable in that X vector. Well, if you actually go back to our invertible matrix theorem, if there is a free variable for that system, and if we can find a non-trivial solution, we know that A is not invertible. So that means, by the invertible matrix theorem, A is not invertible. Okay, now this works both ways. Okay, if A is not invertible, then we know from the invertible matrix theorem that A times X is equal to 0 has a free variable, which means that A times X is equal to 0 has a non-zero solution, which must mean that 0 is an eigenvalue of A because it would satisfy this particular equation. Okay, so it works both ways around. So these are actually double arrows here. So we know that 0 is an eigenvalue of A if and only if A is not invertible. So if A is invertible, we know that it cannot have a 0 eigenvalue. Okay, it works both ways. And that is the end of that proof. So that is 5.1. So we've started to look at this particular formula, and it is a really important formula to remember as we go through the rest of chapter 5. If lambda is an eigenvalue with an associated eigenvector x, then we know that A times X is equal to lambda X. Okay, so remember that formula as you go through this. There are some extra examples that you can look through in the textbook, and as I said, there's a quick theorem that I went through to do with triangular matrices. If you want to look through the proof for that in 5.1, you can, but we will be looking more at that when we do some of these calculations. It will become more evident. If you have any questions on this stuff, please let me know, and I will see you in the next video.